Okay, thank you for attending this talk. My name is Juan Suarez. I'm a software engineer working at Igalia, specifically in the graphics team, where we are working mainly on driver developments. In my case, I've been involved with Mesa since 2016, almost 10 years. Well, 10 years actually. First involved with the Intel drivers, with the old i965 drivers, which is now totally deprecated, and later moved to work with the Raspberry Pi drivers with Chema in the Raspberry Pi 1 to 5. And I've been also working as a release manager for several Mesa releases. So, what's the motivation of this talk? Well, mainly during the years, there was several talks discussing topics related with Mesa. For instance, there was like talks about status updates of the drivers, like Chema did now, and there was some talks about specific components of Mesa, like the one that faced this morning. But actually, there was never a generic talk about exactly what is Mesa. And I mean, I know that probably a lot of people already know what is Mesa, but in the graphics, there are probably people working with in the graphics that doesn't know exactly how Mesa works behind curtains. So it would be interesting to explain them, and also to the broad audience in the internet that is watching this talk. So that's the reason why we are giving this talk, and hopefully at the end you get a better idea of how Mesa works, and if you are not contributing to Mesa, maybe you get motivated for you to contribute. So this is more or less the outline of the talk. We are start with explain the difference between user space and kernel space drivers, which is, is part of required for Mesa. Then a bit of history. So we basically understand what is why Mesa is it has the key to have nowadays. Then a bit of technical discussion of what is the architecture, the main components, showing a small example of what happens behind curtains, like when you draw something, what's happening until the pixels end up shown in the display. And then at the end, a bit of like how we are in Mesa testing all of these things, and how you can contribute and final conclusions. So, difference between kernel space and user space driver. Well, when we usually think about a driver, we think about this very small piece of code that's running on the kernel, and that basically helps to interact with a hardware, like a disk or a USB driver or whatever. And in the case of GPUs, is not different. I mean, in GPUs also you need a driver to handle to interact with the hardware itself. The big difference is that the GPUs are really, really big monsters. Are very complex devices to work with. Just an example, you check the programming manual of the Intel Skylake, which is a GPU from 10 years ago, and it's not the much powerful one in the market. Yeah, basically this programming reference is like 6,000 pages long. So, and there are a lot of small details like if you do this, you don't do that, can do that, a lot of iterations, a lot of very small details that makes very, very complicated program the hardware. So, nobody wants to do that. I mean, unless you want to write a very, very specific application for a very, very specific device that does very, very specific things, you never are going to use the hardware directly. Rather, what you want to do is write your application using a well-known API like OpenGL, Vulkan, whatever, and then let some part of the software you don't want to implement to deal with the hardware. And basically, this is where Mesa enters. Mesa is a framework that helps to write drivers that reside in the user space. And the main objective is to translate this OpenGL API, Vulkan API, to something that then can be submitted to the kernel, something that is very specific for each of the GPUs. usually there is like as we depend on each GPU. Usually we have different drivers inside Mesa that cover different GPUs. Usually, it could be that you have like different drivers for the same family. For instance, in the case of the Raspberry Pi devices, which is basically Broadcom GPUs. For Broadcom, for the GPUs that runs in the Raspberry Pi 1 to 3, there is a driver. And then for 4 and 5, it's a different driver. Why? Because basically because even when the same Broadcom GPU, even in the same family, there can be big difference. And sometimes you need to deal there with different drivers. And well, also because handling OpenGL API is quite different from handling Vulkan API, so you have two different drivers that basically are sharing the same code because the end is the same hardware. This is a Raspberry Pi 4, for instance, hardware, but they are separated. So Mesa, as I said, is a framework because you write the drivers, and you write them because Mesa provides a lot of tools and utilities and everything you need to implement the driver. It makes life easier. For instance, you need to compile shaders. So compile is, it requires a lot of steps, something like that, and well, Mesa provides like a shared compilation compiler and things like that. So to better understand how Mesa is like it is, let's do a bit of history. So Mesa started was working by Brian Paul, which is still contributing to Mesa, in 1993. The first release was in 1995. And the idea was, okay, let's take an OpenGL 1.0 application and translate all the API to something like I can see in the X server, right? So basically it was translating all the OpenGL to calls to XLib. So basically you can show the index server. So in this sense, the first version of the Mesa was like a software rendering device. And the reason was because, in the 90s, there was no GPUs available for consumers. The GPUs were quite expensive devices. It was like a Silicon Graphics device. It was quite expensive, so not for profit, but allow people to deal and try OpenGL in their normal PCs. But it's still, it's not hardware accelerated. Then, in 1997, 1996, I don't know exactly the year, there appeared the first GPU card intended for the market. It was the 3DFX Voodoo. And, well, it didn't work, it wasn't using OpenGL, but a proprietary library, which was called Glide. So it looked quite interesting to basically, like we translate the OpenGL to XLib, was using to write OpenGL to use Glide. So in the sense, this was in Mesa 2.2, and it was like the first popular OpenGL driver that was accelerated. So people can use OpenGL applications and was really accelerated. Still, it was a wrapper. The Mesa didn't access the hardware directly. It was like use a proprietary library. And so, yeah. Then, in 1999, another milestone was the introduction of DRI, which is the rendering interface, which basically allows to access directly to the hardware. You don't need the wrapper or proprietary wrapper. And the first device was the 3DFX Voodoo, but with this, I started to appear a lot of drivers for different brands. It was like Matrox, Intel, was for AMD, for the all 80 Rage devices, 3D Labs. Were quite a lot. I only show a few of them. So, what was the situation now? Well, fast forward, in 2008, the situation was like, we have OpenGL, which have multiple versions. We have multiple drivers. OpenGL is quite heavy API when you are going to implement because it has a lot of states, a lot of things. And I mean, there are a lot of, each driver need to work on its own. And probably a lot of, they are all of them solving the same problems in each driver. So in this moment, Gallium was introduced, which basically tries to abstract all the common parts that are required to do in OpenGL, and just let each driver to do a specific job that depends actually to the GPU, depends on the GPU. Nowadays, all the drivers are using Gallium, all of them. No drivers nowadays are implemented OpenGL, that's using Gallium. So this is a very important moment of the history of Mesa. Then, well, the next was like in 2016, appeared the first Vulkan driver, which was the Anvil, which was implemented as by Fed. It was released in Mesa 12, but sooner, after that, it was introduced RASVIC, which is basically the driver, the Vulkan driver for AMD GPUs. So now, what happens nowadays? Well, the current Mesa basically supports multiple APIs. The well-known are OpenGL, OpenGL in all their versions, but also it's Vulkan, but it's also OpenCL, and there are also other APIs like VA API, which is video acceleration, and AGL. We have multiple drivers for multiple devices, like, for instance, ISL Crocus, which is for Intel hardware, Radeon C, which is for AMD, Nouveau, which is for all NVIDIA hardware. Then for Malice, Qualcomm devices, there is for Broadcom, Vivante, and Sahek, which is for basically for Apple M1 GPUs. Then we have also Vulkan, a lot of different Vulkan drivers, again, for Intel, for AMD, NVK, which is writing in Rust, is for the newer hardware, for NVIDIA hardware. PenVK, which is for Mali, Broadcom, again, Qualcomm, Honeycrisp, which is the Vulkan implementation for the Apple M1 GPUs, PowerVR, and so on. We have also some rendering, which basically implements OpenGL and Vulkan in case you don't want to use the hardware selection because maybe you don't have a GPU, but you need to run Vulkan application. In this case, Element Pipe and Lava Pipe are the most efficient ones. SoftPipe is there because it's like a reference driver. When you want to implement the driver in Gallium, it's like a reference driver to follow. And then something very interesting are the layer drivers, which are like drivers that works on top of other drivers. For instance, the most common, well-known is Sync, which basically implements OpenGL on top of Vulkan. And it's interesting because, for instance, in the new NVIDIA GPUs, we only have MBK driver, which is Vulkan, but then you use Sync on top of MBK, so you get for free OpenGL drivers working on the GPU, on NVIDIA GPUs. Simply, we have OpenGL on top of Direct3D for Windows. We have Cosmic Crisp, which basically supports Vulkan on top of Metal. So you have you can run Vulkan in any Apple device. And then we have Vigil and Venus, which is basically OpenGL and Vulkan for virtual machines. Like, for instance, Venus is like you can run Vulkan is a virtual machine, and it's accelerated because it uses the host GPU. There is also, as I said, OpenCL, which is nowadays RustyCL. The idea is here that if you have your driver, OpenGL driver, is implements, which is using Gallium, and you support the required, implement the required bits, then you get for free an OpenCL driver. And then something quite new is Teflon, which is basically a TensorFlow layout delegate. that allows to use TensorFlow to run the hardware-accelerated AI application. In this case, we have these NPUs like the Rockchip, Vivanti, and things like that. They are also based on Gallium, so basically it means that you need to implement specific functions that Gallium requires, and then you can use these devices to accelerate your AI work. Now, so let's see the components of Mesa. So this is a simplified diagram. I just remember a lot of details and all that thing. A lot of parts that are not interesting for this. For this talk, because we have not much time. So first of all, we have the OpenGL and Vulkan application, right? And the first thing is that these applications are not going to be linked against your driver, right? Basically, they use a loader, and the purpose of the loader is to find the proper driver and then hook the redirect the operations, the OpenGL functions, to the specific driver. This has the advantage that you create the applications and you can choose different GPUs to run your applications. Usually the loader will choose the best one for you, but you can change it, or you have multiple GPUs. You can choose, okay, I want to run with this GPU for this application and with this other this application. So then on the left, we have the OpenGL drivers, right? And as you can see, is much more complex than the Vulkan, right? And the reason is because OpenGL itself. OpenGL is for the 90s. It's a very, very old API. And when it was created, it was like GPUs were thought like machine states, right? And OpenGL was designed with that in mind. And that design kept until these days. And what I mean with a state machine, well, just basically means that, for instance, you want to draw an example. You want just to take a texture sample and draw it in the frame buffer. There is no, that operation is not explicit in the sense that you don't have a function that say, you pass the texture, you pass the frame buffer, and draw. Rather, the procedure is you bind a texture in the OpenGL, so you need to think like OpenGL is a state machine, transit to the new state where now I have a texture bound, right? Then you bind with another operation or another call to OpenGL, you bind a frame buffer. Now again, I have another state where I have a frame buffer and I have a texture. Now, any operation that you are going to do from that moment on will be use these two bound resources. So now you say draw or whatever, or sample, and we will use these resources. If you want to change the frame buffer, you need to do another operation, and then again, another transition, another opinion. So there are a lot of states that need to be handled. And the other problem is that if you read the OpenGL spec, this happens in OpenGL or Vulkan, in order to execute operations, you have to match some preconditions, right? For instance, you want to sample a texture, you need to have a texture bound, because otherwise you can't sample it. And the OpenGL spec is very specific about if you don't have something, the error you need to do. You can. It's not like, okay, if something doesn't fulfill, whatever can happen. No. It's say, okay, if you don't have this condition, then you need to write this specific error. So if your specification, a lot of pages are just saying about the errors you need to submit when there's something that is not fulfilled. So this means that a lot of time, a lot of resources are spent validating that you can execute the operation and report the proper errors. So again, all of this stuff it doesn't matter if you are running GPU AMD or you're running Intel GPUs. You need to do that, and all of this part is quite common. So that's the reason why they have this quite complex part. Just zooming it a bit, there are like a first layer, which is this comes from from the older versions. This is like a very thin layer, which is basically like is the entry point for the OpenGL API. This layer is quite thin. Basically, what it does is kind of validate that you can run the operation. I mean, all the conditions are fulfilled. And then, if it happens, then move to Gallium, which is this handles all the complexity of the state machines and things like that. So the way this works is like when you write your driver, like Iris driver, basically you are going to create structures for Gallium. I mean, there's an API to do that, things like that. And then basically this Gallium provides like hooks that you need to just implement them. And these hooks are the specific parts for your driver Gallium is going to use just when something that it really depends on your driver, your GPU. I mean, for instance, you are going to draw, at the end, you need to use the GPU. So there will be a hook for drawing when all the state machines and all the things are managed. Also, the drivers provide like capabilities, so they form like what kind of features they support. So Gallium can decide what to do, depends on the dev. For instance, is a way of Gallium saying, okay, I'm supporting OpenGL 3.1 because my backend, my user space driver is telling me that I support this kind of features. But at the end, the main work is done in the Gallium part. Then in the right part, we have the Vulkan drivers. I mean, this is much more simple because Vulkan is a modern API, is explicit, and there is no validation in the sense that, I mean, API also have some requirements, like you need to have fulfill these requirements in order to execute the operation. But the good part is that they say, if you don't do, whatever can happen. I mean, it mandate to validate. It's the user needs to validate, ensure that everything goes is correct. So this happens that you don't support that. It can happen that you can crash or GPU reset or GPU hang or whatever. I mean, fortunately, I mean, it's quite difficult to implement an application and not have errors. So in the case of Vulkan, there is an intermediate layer, which is called the validation layer, which sits between the Vulkan loader and the Vulkan drivers. Basically, what it does is like when you call a Vulkan function, this validation just intercepts the call and basically tracks all the states and is ensuring that you fulfill all the requirements. And if not, it will tell you, okay, you are in fulfilling this requirement, and give you even tips about, okay, you are doing this, but this is not very performant, so that. But the point is that all this validation thing is not done by the Vulkan driver. So easy to implement, faster when you are running in production the applications. Still, I mean, there is some parts that are like common. For instance, still you need to create like a dispatch table, which basically is like when the Vulkan function which function should call from the driver itself. I hooks all the chains of the calls. For instance, there are like a common buffer recycling. You can reuse common buffers. So the Vulkan runtime utilities basically is like a common service between codes as a service, because actually is not a service as a web service. But it's something that the driver can use to make life easier. For instance, I don't know, I'm thinking now, for instance, timeline semaphores, which can be provided through runtime, through utility, that if you don't support that, it can be implemented using the normal semaphores. And so you can do that. Nowadays, I mean, all the drivers are using this Vulkan runtime, because it really makes the life easier, because quite a lot of things are handled by this runtime. Then we have the shader compilation, because again, all the modern applications need to compile shaders. So this is the part that just receive a GLSL shader or SPIR-V, if you are using Vulkan, and transforming to the final assembly code suitable for your GPU. again, there are some parts that are common to all the drivers, but other parts are specific to the backend because the assembly really depends on each GPU. Each GPU has its own assembly, and even for the same GPU, depends on the family, there are some changes and things. So basically, this is what the shader compiler does. We will see that later in a more detail. And then, once we have everything, we have the kernel part. So in this case, basically, there is like a library which is used to talk with the kernel drivers, which is called libdrm, DRM by Direct Render Manager. And so, yeah, basically, when your driver, the Vulkan or OpenGL driver, has everything ready to be executed, it's like everything in memory. Basically, it sends that to the libdrm, which is in the kernel, and then each of these specific drivers, basically what they do is do the scheduling the job. The job needs to be executed by the GPU. So basically, do things like, okay, let's schedule the job, prioritize, touch the right registers or whatever. So the job is started by GPU. Monitor when the job is finished to tell the user space driver, okay, I'm finished. It's waiting for a signal. If something wrong happens, which a lot of time happens, we need to reset the GPU, do that. I mean, a lot of things that are required to do to finally execute the job. So I think, when we see the components, we can go a bit of more detail on what happens behind the curtains when you call a function, OpenGL function or a Vulkan function, what happens inside Mesa. Okay, so first of all, I'm deleting a lot of details, small details, so I just like simplifying a lot of the code. I will simplify a lot of the tool chain of the chain of the calls because there are a lot of calls. So just give you an idea of what is happening here. So this is for instance, when we call GL draw arise and the loader find the proper driver, basically this is the first function, the entry point for this operation, which is called Mesa draw arise. And as explained before in the architecture, the things it does is update the states, right, and validate that things are correct. If something is not correct, it returns an error, sets an error and it returns. And if everything goes fine, then start the draw itself. The draw itself is still in the Mesa layer, but again, it does several registers, something like that, structures, sorry, and then it calls the state tracker to prepare draw and call the draw value, which is basically is the Gallium part that is in charge of executing the draw. Again, the draw Gallium do a lot of things. I call CSO draw VBO. CSO is an object that keeps a constant state object that keeps the states of the full machine, and it basically calls that. This now is everything in Gallium. Now I want to go ahead because if you check the stack, is like 20 calls, and I want to show 20 functions. Okay, so bear with me with that. But at the end, it ends up running the function of draw function of the specific GPU. Right, at the end, need to do that. In this case, I'm showing the case for the V3D, which is the Broadcom, the OpenGL drive for the Raspberry Pi 4 and 5. From this moment on, each driver handles the operation really depending on the GPU. So each driver has implemented in different ways. And I'm going to show how the OpenGL, how the V3D driver does. But more or less, the idea is that all of those drivers will, like, at the end, like, the outcome is quite similar to all of them. It's like, you create a bunch of command streams or jobs, which are basically like a lot of structures where you configure, you put the values in the structures, that contains addresses, it contains assembly code, a lot of things that are the things that the GPU configures the GPU, and then put that in a buffer memory, and this is going to be dispatched to the kernel, because that is what the GPU is going to read and do the execution. So you can configure a lot of things there. More or less, I mean, of course, each driver has its own structures, but at the end, it's not more or less the idea of all the drivers. For the case of Vulkan, in the case is BK CMD draw, as I said, it's much more simpler, and almost the call is directly. I mean, the entry point is directly offered by the hardware. In this case, is the V3D. So unless you have this validation, calling the BK3D to V3D CMD draw, is very fast. There's no heavy operation on that. So in this case it's very simple. And as you see, we start to draw. I mean, there is no validation at all. Again, I'm not going to show how this keeps continuing, but again, it depends on the hardware. But at the end, as this is the same hardware, like this is the Vulkan for the same hardware as the previous one, more or less the outcome will be similar. I mean, it will like a bunch of structures that put in the buffer, assembly code for shaders, and then submit that to the GPU to be executed. Now, before we draw, we need shaders. I mean, as I said before, this structure contains shader assembly code. And if you use OpenGL, the shaders are basically writing in GLSL. If you use Vulkan, it's working in SPIRB, which is a much lower level binary language, which is basically created from GLSL or other high level language. But at the end, either one or another, you need to compile that to generate a final assembly code. In the case of GLSL, there is like a step where there is a parser inside Mesa that parses the code, generates an intermediate language, and then that is converted to NIR. In the case of SPIRB, it's basically just converted directly. It's like a match one-to-one that converts SPIRB to NIR. NIR is a language used by Mesa, which means new intermediate representation, which is, I think, was introduced in 2015, and this is the language that is used by all the drivers mostly. And this was designed for the GPU, so it matches very well to the GPU. And so it is that you transform that GLSL or SPIRB to NIR. This is an example of NIR, a piece. And this NIR is transforming in SSA form, where a single static. Well, I don't remember the acronym, what it means. But the thing is that this is in a form that you can apply a lot of optimizations that are very well known. From the compiler world, you can apply a lot of those optimizations. Examples are like algebraic optimization. Like, for instance, you have an operation that says A plus A. You can simplify that as twice A. It really depends on how it is faster or not. Common subexpression elimination, dead code elimination. Like if you have a code that is never going to be executed, it removes that. I mean, all those kind of optimizations are applied in this NIR step. It's also applied lowerings. Basically, lowerings is replacing an operation by which is more complex, by a different, more simpler operations. An example is, for instance, if you have you need to compute the sign of a number, and your hardware doesn't support the sign by itself, you can replace the sign by a Taylor expansion using more simple instructions. So basically, the lowerings do that, and there are quite a lot of lowerings that can be applied on the NIR, and a lot of them depends on your hardware. I mean, that's the reason why we have this capability. For instance, that is that you okay, how to support this? Okay, then I can execute this NIR operation. Otherwise, I need to lower and transform that. So, as I said, This is common for all the drivers. All drivers get benefit from this kind of optimization. So if you add a new optimization, all there will be get this optimization for free. Then, once you have need to transform. We still need the assembly code for GPU. And basically, what we do is we have an optimal NIR, was passed through all these passes, and send it to the specific driver. Because now, for that moment on, only the drivers know exactly how to transform that in the specific assembly code for that GPU. Again, I'm showing an example with the V3DB, with the GPU for the Raspberry Pi 4 and 5. In this case, the NIR is converted to another intermediate language. It's called BIR. This BIR is more suitable, more suitable for the GPU. It uses instructions that are more than the ones that hardware support. Okay, and here we do more optimizations that are very specific to the BIR. We do scheduling, reordering instructions, and things like that, until we get optimized BIR. And then this BIR is converted to QPU. It's called QPU, which is basically this is the raw assembly for the Raspberry Pi 4 and 5, which basically has two lines of execution, one for multiplication, another for arithmetic operations, and can run in parallel. So this is very specific to the Raspberry Pi 4 and 5. Again, if you go to another device, it's quite different. For instance, in the case of AMD, it uses ACCO, which is the backend compiler. There are other cases that are using even LLVM. They use that as their intermediate language, and they do a lot of operation. This completely depends on each of the GPU. Okay, now we have all these jobs and command lines. As I said before, we have now the assembly, and I need to submit to the GPU. As I said, this done with through libvrem, and basically what it does is each GPU will take its jobs, it submit to the GPU, which basically sometimes means, for instance, in case of the Raspberry Pi, it means that okay, I'm going to write in a register where the address of this buffer, and write another register that says, okay, start to get execute the job. There's another register that says when the job is finished or not, and there are signals to say, okay, the job, there was like an interruption because it was a crash or whatever. Everything is managed. There are newer GPUs, for instance, are able to schedule through hardware, have components to schedule the jobs through hardware, but at the end, everything is executed until you get this beautiful triangle and screen. Okay? So more or less, this is a simplification of what happens behind the curtains when you run the OpenGL or Vulkan. Now, from a point of view of the project itself, how to test and contribute, how we test and contribute things. Okay, so basically we use GitLab. Where we basically report fixes and report issues. Patches are basically merge requests that you submit. It will be reviewed by people, by very smart people, and they can either accept it and say, okay, this is fine, accept it, or maybe which is most of the times, is okay, you need to fix this, you need to fix that, or maybe you need to, for instance, I edit a merge request to fix something in my driver, but then that change is broken on the driver. So it will say, okay, be careful, review that because you are breaking other drivers, so you need to review. So this is an iteration process. And when everything is accepted, the merge request is not directly merged, but is assigned to a merge bot. And basically what merge bot is like, it has a queue of merge requests to be merged, and what it does is, it takes the first merge request, replaces against master, upstream, to the main, to the top, then run several tests, and if everything goes fine, merge it. Okay, if something doesn't go, rejects until, okay, something is wrong. Next merge request. and so on and so on. Why does that? Because if you try to do the merge request all together, maybe this works, but together it will fail. So this is very why this is executing one by one. Okay, and how much is tested thing? Well, the first thing is that it will rebuild all the tests, all the drivers that are affected by the merge request. Sometimes there is a merge request that touches, for instance, the Vulkan code, so that is not going to affect the rest of the drivers because the drivers don't use Vulkan. But for instance, if you touch something about NIR itself, this NIR is used by all the drivers, so all the drivers need to be compiled. And then basically it executes a lot of different test suites. Basically it executes Piglet, which is a set of community test suite for OpenGL. But we also run OpenGL CTS and Vulkan CTS, which are the conformance test suites for the driver. Running Vulkan CTS can take a lot of hours, okay? And we don't want to have a lot of hours until something is merged. So what we do is a lot of different actions to make the things work faster. For instance, instead of running one test, like Vulkan CTS run one test each time, in our case we run, like, for instance, your GPU has 4 CPUs, 4 cores, we run 4 tests in parallel, which make things faster. Then we distribute the execution in multiple GPUs. For instance, for the Raspberry Pi, for instance, we have 8 or 9 or 10 Raspberry Pi 3s. So when you running a test, the subject affects the Raspberry Pi 3, we distribute all the jobs in all these devices. So they are run in parallel. And then we also run a subset of tests. So more or less the idea is that to have everything executed in 15 minutes, more or less, right? And it's happening, I mean, it's just X, we merge. Then, of course, every night we run like a nightly pipeline, which basically is, okay, now I have time. We are not blocking all the merge requests. That's the reason why we run this in 15 minutes. But so let's run all the tests. So in this case, we run a more comprehensive test. For instance, we run maybe the full CTS. It can take maybe 1-2 hours. But I mean, we have time. We'll do this only on the night. And if everything happens, well, people will see the next day, okay, maybe my change passed there, but it was a very specific corner case or specific test that didn't pass. Well, you need to work on a fix, and well, that's all. So, as conclusions, Mesa is like basically a translation between different graphics APIs and the hardware. For the case of OpenGL, it provides all a full state machine tracker and multiple utilities that implement the drivers, that helps to implement the drivers. It also provides a very comprehensive set of tools for compiled shaders, provides a lot of optimizations and helpers just to get the final assembly code. NIR is the common language used for mostly all the drivers nowadays. And then all the work is submitted to the GPU is in libprm. Okay. So I hope you have now better idea, not deep, but at least some idea of what happened behind the curtain with Mesa, and I hope that you can start to contribute to Mesa if you are not doing that. And that's all. Questions? What are the bigger challenges for Asahi, right? Okay. Yeah, so I'm not working on Asahi, so let's take this with a grain of salt. But I think one of the problems is that, well, Asahi implements the full OpenGL API. And the OpenGL API, not the ES, but the API is thought for desktop devices, but mostly the Apple M1 GPU is like a big mobile GPU. So there are a lot of features that are not supported by the hardware. So you need to do a lot of things to that. And then on top of that is that most of the things require reverse engineering because there is no documentation of how to program the GPU. So you need to do a lot of like tests to figure out how this thing works. Which is, I mean, fortunately in my case I don't do that, but it can be very, very challenging. I need a lot of experience do that. Fortunately, the person that is working on the Asahi, which is Alisa, she has a lot of experience because she was doing reverse engineering for other drivers. So she has a lot of knowledge how to address it. But yeah, the more complicated parts.
Do you have any particular advice for someone who's been lurking for a while but wants to actually start contributing to Mesa?
Yeah, well, I think. Oh, sorry. Yeah, if there's an advice for someone that would like to start to contribute to Mesa, right? That's the idea. Well, yeah, the thing is in Mesa there are quite several issues that basically they are like attacked with easier. You can start to do that. So that I will start to do that. Then another advisor is that it's easier, usually, to start with hardware that you have documentation. Like if you need to do things and then you don't have the documentation for the hardware, it's quite complicated. So for instance, in this case, Intel hardware is public documentation. I mean, it's a complex device, but it has public documentation. And then, of course, asking, because, I mean, the people in the community would like to get more contributors, and people in the community are very nice and polite. So I think if you have doubts, you can ask. There is like an IRC channel, you can ask questions, so you can submit them. So, yeah, basically it's just a matter of starting with something simpler. You have the code, you can check the code, you can do experiments with that, you have tests to see what happens in this or that, you have GDB or whatever to do tests. So yeah, basically that's my advice, just to start, basically. Yes?
So libDRM contains hardware-specific stuff, and there's also hardware-specific stuff in the user space box.
Yeah.
If you have something that's specific to your GPU, how do you decide where it goes?
Yeah, the thing is, in libDRM, it has like common functions that are common for all the. Okay. The question is that libDRM have a specific function for specific hardware. So basically, how we basically manage, because there are like multiple drivers and multiple different structures, right? Okay. So yeah, basically, libDRM is has like a common part. These functions that are common for all the drivers. Basically, like for instance, creating memory, assigning memory, things like that is more or less the same, right? But then it has backends, like different backends, and these backends are implemented with IOCTLs, where you pass like operation, okay, and then the structure or whatever. And this is very specific for each driver. So each driver, when it loads libDRM, actually it loaded the DRM for its own backends, for its own drivers. So for instance, when we use the Vulkan libDRM, there is like a libDRM / I don't remember the name, V3, I think, or something like that. And that contains the IOCTLs with the code specific for the app. So now I know basically the driver, the user space driver knows, okay, if I want to submit this job, this is basically the API I need to use. IOCTL with this, but the structures of everything I need to know is well documented. It's like in the speak for this DRM. So it's like there are two parts on the libDRM.
Can I check that I've understood that the API between the user space bit and libDRM is potentially it's got overlapping bits for different hardware, but they can have like a different API.
Yeah.
Okay.
Yes. I mean, for some operations are the same.
Sure.
It's like you have like DRM.h, which is a common function, and then you have DRM/mbk.h or DRM/asahi.h or whatever. And that's the specific parts of the. I mean, the functions are quite similar because all of them are IOCTLs, which is basically the common way of communication with I/O. But yeah, what service offers really depends on each hardware. So a lot of time we need to add new IOCTLs in the ORM when you need to speak newer things that you need support for the kernel part. So you add a new IOCTL, and that's all. And your driver start to use. I mean, you need to check if you have the proper kernel version that support the IOCTL, but it's up to the. I mean, that's part of the driver to check if you are running the correct kernel or not. Yep.
Sorry if you might have already answered this in the second to last question. I wanted to ask if you have merge requests for both classes and the merge tests that run after this. Is there many instances of merge bot tests failing? Like, is it common for?
Yeah. So if you are like a statistic about the failures of merge request.
Yeah, like the research, like would it be common to fail those tests after this? Like, can I run it locally and expect it within reasonable parameters, basically the exact same outcome?
Okay, I'm not sure if I'm getting the question correctly, but I understand that if something fails when you are running the merge request, this pre-testing thing, if something fails, that if you can do something, I mean, in your local, you mean your local computer to.
Yes, as in, if things usually go smooth between merge approval and merge test.
Mm-hmm. Okay, so I mean. Yeah, I mean, sometimes you are working, everything works fine in your computer. You submit to the merge request, and then something fails. Okay, so I mean, really depends of. I mean, sometimes it's obvious what is happening. It really depends, but sometimes really depends. I mean, maybe the failure only fails in a specific driver that you don't have this driver, and I mean, you can check the code and guess what is happening, but sometimes what we end up doing is like ping the person by maintainer of this, say, okay, I do this, and this is failing, but I'm not sure why. Maybe you can take a look all that, because I mean, you don't have all the GPUs in your home. So other time is like you guess, okay, maybe this is the problem, and then you can basically submit a branch, and then force the GPU to execute this code. It happens a lot of times. So you execute using the CI, the OpenCI, you execute the test and say, okay, yeah, now it's fixed. Now I can update my request and things like that. But it really depends on the kind of errors and things like that.
How more difficult does things like Vulkan make your life? Because OpenGL validates a lot of things ahead of time, right? So it's less likely to question the driver because something went wrong. How does that affect like how much you have to be super careful when doing the driver part when using Vulkan? Since that nothing can be validated. Okay,
so basically, is like the question is how much life is more complicated in Vulkan, because in OpenGL it does a lot of things and you do that in Vulkan, right? Okay. Actually, it makes things more easier for multiple reasons. Okay, first, yeah, you don't need to validate anything. I mean, you assume that everything is correct. If something is wrong, the problem is not you. It's not on your side. It's in the developer side. Unless the requirements are fulfilled and still something is wrong. Okay, so in that case, it's more simple. And then the Vulkan API, which is basically what the thing you are going to implement, I mean, is big, is very verbose, but at the same time, it's more near to what actually the GPU is doing. In the case of OpenGL, if you want to do things really, really fast, you need to do a lot of assumptions and tricks and things like that. And part of them are done by Gallium, that's why it is very complex. Another part needs to be done in the driver. So in this sense, I mean, the thing is that the OpenGL driver is not the same like your hardware, whatever your hardware. You need to do a lot of absorption, a lot of implementation. Like that. So in this sense, when you write the code in the Vulkan, I mean, I understand that writing Vulkan application is more complex because you need to write the whole Bible. But when you see the functions, you say, okay, this is more similar to what the GPU is doing. So I don't need to do any kind of assumptions or or how I'm going to abstract this concept in using Paint to implement this in my GPU. So in this sense, it's more simpler. Okay, I think that's all. Okay, thank you very much.